Alright, so we're going to be taking a look at something called the systems approach for free body diagrams. In the past couple of videos, we've been looking at mostly just one object of study, where we just used the Newton's second law for just one object. But in this video, we're going to look at scenarios where there's multiple objects, and we're going to take something called the systems approach, where we treat them kind of together at the same time. So this is the very first case I have drawn here. We have a little mass m and a big mass m. And we have the big mass is obviously is greater than the little mass. The acceleration is going downwards, so we see that it is going to be accelerating this way. And we just want to kind of find an equation for the acceleration for this, right? Try to describe it in terms of these masses and any force between them, any gravity, anything like that. Okay, so the first thing is probably to notice is this pulley, right? The pulley has one job in this case. Usually pulleys have one job. It's just to redirect forces. In this case, it redirects the tension forces. It usually redirects tension forces. As you can see, the tension force is this way, and then it also is this way, right? It redirects it. And then another thing is that the key thing with the systems approach is to treat them as one thing. So we also want to kind of treat a direction as one thing. We don't really want two independent directions like we did before. So the way we do this, actually, I wanted to find this way, so this along this line. So we have initially going right, but then it curves down. I want this way to be positive and this way to be negative. So let's look at any force that happens along this direction. We don't really care about the other one, like especially like this one here and this one here, because they're not really involved with the motion anyway. So we're just going to be focusing on the things that happen along this line. So this is the key part, I would say, this part. So let's begin. Let's draw the free body diagram of just the forces that we care about, right? So only this tension force. I'm going to do it in blue. This is the little mass, and this is the tension force, right? And then for the big mass, capital M, we have the same thing. We want to draw the free body diagram of what's happening along this line, and we actually have two forces, and what they are is that it's the mg. I'm going to write it as capital Mg because we're talking about the big mass. And then we have a tension force, right? And one thing to always remember that if you have tension between two objects, these tensions will be the same. So I'm going to show with the same letter, T, same letter. So now here's where all the stuff happens. We're going to write a Newton's second law equation following this convention where going rightwards here and downwards, curving here, is the positive direction. So let's look at each of these forces and find out if they're positive or negative. Not too bad. So this is a positive force. This is happening along the right side. This is a negative force, since if you go this way, it's negative, and then this is a positive force, right? So we have T minus T, and then we have plus capital Mg, right? Those are all the forces. And then it's equal to ma, but the m is actually special. It's actually the total mass of the system. This is why we call it the systems approach, because we want to take into account the total mass of the whole system accelerating, not just one object. So I can write it as this, right? The sum of the masses. And then we see something pretty interesting, that we see that the tensions cancel out, and that's usually the case with the systems approach, especially with Atwood's machine, that the tensions will cancel out somewhere. And now we can just solve for A, right? We can just solve for A, and let's see what we get. I'm going to draw it in blue. A is equal to, so if we divide it, we get capital Mg divided by M plus M. I'm actually just going to write it like this. Maybe it'll look much nicer. And this is the systems approach, where we just found the acceleration of this whole system, or specifically, if you want to think about it, the acceleration of this block and this block. And it's defined by this. Whatever the mass of the big object is, divided by the sum of the masses on the bottom times the gravity. So we want to look at that. So now we're going to look at another example of using it with an Atwood's machine as well. So here's case 2. So it's another version of the Atwood machine. This time there's 2 pulleys and it's across the table. So this is actually very similar to this problem right here. right? Except we have it not on the table, it's now also on here. And I also want to make this statement that the mass, the capital M, is also bigger than the lowercase m. And I remember doing this problem like 2 years ago. It was a very interesting solution. This is the problem that first introduced me to the systems approach. So we're going to continue doing this. We're going to look at the free body diagrams of these two objects, which we should do the capital M here. So capital M, we have its weight, mg, and then the tension force. And then we have the little mass, right? Let me draw another one here. The little mass, whose weight is like this, and the tension force is like this, right? This is the little mass. And then we want to continue with our direction of motion, right? Usually I like to define my direction of motion as where the acceleration is happening, so it makes things a lot more easier to think about. So since the mass on the left is bigger than the mass on the right, I'm going to define this way as the positive direction, right? So in this first section it's actually kind of up and down, and then the second one it switches. So let's look at that. So with the little mass, if we were to go by this convention, this mass here is a negative mass, and this force here is a positive, right? This force here is negative because it's opposite of the direction I chose, and then the tension is positive. And then while in the other diagram, this force is positive and this is negative, so it kind of switches. Just keep that in mind because of the direction I chose. So now we're going to continue with the Newton's second law. So the net force of the system is equal to the mass of the system times the acceleration. Right? So now we just want to sum all the stuff. So let's start with here. So we have the mass of the big object minus the tension force. That's all about the capital M mass. Those are the forces. Now we want to do the little ones. We add the tension, and then we subtract the little mass. Like that. And then it's equal to the mass of the system, so I'm going to replace that with the sum of the forces times A. And then now we just want to simplify through. Usually with these problems we actually want to find the acceleration of the system. So we're going to actually cross this out. So we want to divide by A. So let's see, capital M, G, minus lowercase m, G, divided by M cap plus capital M equals acceleration. And then we can, I guess, make this look nicer and factor out a G, since there's a common G on both terms. So it's equal to the subtraction of the masses divided by the addition of the masses, which is pretty interesting to me. This was an interesting result when I first came upon it. And I guess we can I'm going to rewrite it here just to continue this idea. There we go. So that's the acceleration of this whole system, and we took the systems approach to solve it. Now we kind of want to look at a small variation and think about something that, if I were to change this just by a little bit, think about how does this equation, I guess, change in response to it. Alright, so here we have case 3, and the difference between this one, I just redrew it in to make it see where the boxes are. The difference between this one and the previous one is that I just added a box on top of the table. And we want to kind of answer this question: how does the acceleration of this example compare to the previous one? So again, we can take this approach, right, the systems approach, and define this way as the positive direction, right? And I'm going to do this pretty quick since we already kind of done an example of this. The F of the net force of the system is equal to the total mass of the system times its acceleration, and we want to kind of compare them together. So we have, so here, let me draw it in orange. We have this one, we have one here, we have one here, we have the tension forces here, a lot of tension forces, right? And basically what we'll see is that it's the mass of 1, right? The mass of 1 times its gravity subtracted by the tension, right? This is all the forces on 1. And then plus, let's look at the mass of the third object, which is this tension minus tension, right? We don't really care about the vertical stuff on the table because it's not part of our direction we're looking at. And then we look at the second mass here. It's the, let me see, I forgot an arrow here. It's the tension minus the mass of the second one. And then it's equal to the sum of the masses times acceleration. So Now we can see a lot of the tensions just cancel out, actually all four of them do, and then we see that M1 minus M2G, M1G minus M2G is equal to the sum of the masses, M1 plus M2 plus M3, A, and then we can solve for A. I'm going to write it in orange, and then we're going to look at the comparison between them. M1, what is this? M1 minus M2, and then divided by M1 plus M2 plus M3. Right, so that's the acceleration for this one. Now we will actually want to compare these two results, right, and see how the acceleration compares with the 3-block system and the one above, the 2-block system. So I have it here. We kind of see that they have a very similar type of format, right? It's G times, on the top we have a subtraction of a mass, and then on the bottom we have the mass of the whole system, right? I guess to be more clear, the masses here, this is mass 1 and mass 2, right? With this is this mass and this mass, and then this is mass 2, mass 1. Just to make it more clear in our comparison when I'm trying to compare these accelerations. One thing to notice that is kind of important is comparing the numerators and the denominators, right? The numerators of both are actually the same, but the denominators are different. In the 3-block system, we have a sum of 3 masses, and in the 2-block system, we have a sum of 2 masses. So I want to make this comparison right here, since M1 plus M2 plus M3 is larger than M1 plus M2, right? That's obvious. And this term happens in the denominator. The acceleration of the 3-block system will be less than the acceleration of the 2-block system, even though they're pretty much very similar diagrams, right? Right here and right here, right? This one's just adding another block, and then we see that even just by adding a block, even with the forces canceling, we have a smaller acceleration because it adds to the total mass when we do right here, this step right here, when you divide it by the total mass right here. So this is just a basic approach of the Atwood machine, and anything with usually more than 2 bodies or even 3 bodies, you can use the systems approach most likely, especially with Atwood machines with the pulleys. You just have to define a direction as not just like a strict horizontal and vertical, almost like a path. You can do that. So we see that it's actually much easier, I'll tell you, than doing it individually and combining them together. Doing the systems approach is actually easier than doing them separately. So that's it for the systems approach. So